Hello everyone and welcome to our 6G event, approaching the era of 6G. My name is Rakesh Tamrakar and I'm a 6G specialist at Vivo Communication Research Institute. At Vivo, we began spearheading 6G research as early as 2019, when we established our 6G research team. Our key purpose is to explore and verify the cutting-edge 6G technologies that will best meet the need of our consumers. To that end, all of our work is grounded in Vivo's user-centric values, which we believe pave the way for better and smarter digital life in future. To share our findings, we have released a range of 6G white papers over the years. Today, we will take a deep dive into Vivo's latest 6G achievements and look into some of the exciting results from our research in the field. We will speak about our latest findings and insights on 6G network architecture and services, convergence of AI and communication, as well as the exciting field of integrating sensing and communication, otherwise known as ISAC. Furthermore, we are also eager to showcase some of our latest prototypes built for 6G and discuss their potential application scenarios. Without further ado, let me introduce our first keynote presentation of the day, Convergence of AI and Communication. I'm delighted to welcome our expert Sun Peng. He's our Director of Transmission Technology and will share more about opportunities brought on by integration of 6G as well as AI. Peng, the floor is yours.
Hello, everyone. I'm Sun Peng, Director of Transmission Technology at Vivo Communication Research Institute. Now, I will introduce our views on the convergence of AI and communication. This presentation will cover three key areas. First of all, I will share with you why we are interested in this area by discussing the benefits of a convergence of AI and communication. I will then share with you a demo video of our AI prototype for communication field testing. And then I will go into more details about our design principles. So first of all, artificial intelligence is the set of technologies that enable computers to perform a variety of advanced functions, including the ability to see, to understand and translate spoken and written language, analyze data, make recommendations, and more. In recent years, AI has achieved great success in several fields, such as advanced web search engines, recommendation systems, human-like assistance, self-driving, generative or creative tools, and competing at the highest level by making strategic decisions in games. For example, the game of Go. At the same time, wireless communication systems are also continuously evolving towards higher throughput, lower latency, higher reliability, and a larger number of connections. Merging these two trends, the International Telecommunication Union has already identified AI capabilities as one of the fundamental capabilities for 6G. There is a huge potential for AI to provide remarkable solutions that meet a stringent requirement of 6G. AI can be used to solve three typical problems in 6G communication systems. The first kind is problems where local hidden knowledge can greatly improve performance, but it is very difficult to use traditional technology to extract such local knowledge. For example, in AML-based positioning, the local radio environment information can be used to improve the accuracy to sub-meter level, while the performance of a traditional technology would be much poorer, with positioning errors larger than 10 meters. Another kind is the problems wherein the optimal solution is unable to be found within practical time limit. For example, at present, the optimal solution is difficult to be found in wireless resource allocation and management due to fast-changing channel conditions, dynamic traffic patterns, and complicated interference within and across cells. To solve this issue, AML-based resource allocation could learn the hidden patterns of complicated interactions between different influencing factors and help to find a near-optimal solution within real time. The third problem that can be solved by AI is related to joint optimization of multiple related functions. These areas cannot be easily solved by traditional technologies, since joint optimization would make the problems more complicated and difficult to be solved. But AML solutions directly observe the relationship between input and output of multiple modules, and thus can jointly optimize these functions. With this understanding in mind, since 2018, vivo has invested heavily into convergence of AI and communication. Our communication technology engineer Shi Sihao and Sun Bule will now tell us more about wireless AI applications. Please enjoy this demo of AI-based channel estimation and our AI prototype for communication field tests.
The convergence of AI and communications is accelerating. The prototype here leverages AI to perform channel estimation and processing in a conventional communication procedure. The computer displays a comparison between a conventional channel estimation algorithm and an AI-based channel estimation algorithm in terms of constellation diagram, block error rate, and throughput of the data received. We can see that the AI-based method can reduce the overhead of demodulation reference signal (DMRS) by 50% without sacrificing the transmission performance. It can thus provide more transmission resources for data. What else can AI do in the communication system? This is our general test prototype for AI-based communication. It collects data related to various types of signals on the physical layer of the mobile communication network to support the training, deployment, and verification of neural networks. We collected data on channel state information in the vicinity of Vivo's Beijing office and completed the verification of AI-based channel compression and channel prediction. It can be seen that in the actual air interface environment, AI-based channel compression and channel prediction can achieve significant gains, which can be used to improve the air interface throughput. We also collected data near the 5th Ring Road in Beijing to validate AI-based mobility enhancements. It can be seen that the mobility data predicted by AI is very close to the real mobility data, which can be used for mobility enhancement to achieve better handover performance. In summary, the convergence of AI and communications will allow our phones to intelligently match a variety of complex environments and ensure optimal communications performance and smooth internet experience anytime and anywhere, including the subway, garages, elevators, and high-speed trains.
Thanks for Sihao and Bule's introduction. Very interesting. With our experiments and research from academia and industry, almost all areas in a 6G system can be considered for joint design of AI and communication. These extensive use cases will need to be taken into account for system design. These use cases cover all layers of communication systems, including PHY layer, MAC layer, layer 3, core network, and so on. Moreover, different learning algorithms may be used for these cases, including supervised learning, semi-supervised learning, reinforcement learning, and so on. And these use cases also require different collaboration levels between network and entities. A future-proof, unified native framework is needed to accommodate all of these different aspects. Otherwise, the communication system will be overly chaotic and non-sustainable. To design such a system, we need to take several things into account. From the perspective of the life cycle of each use case, we need to design unified signaling and procedures for various use cases. From the perspective of AI/ML capabilities, spatial distribution, we need to adopt an architecture that supports various kinds of a distribution of intelligence. From the perspective of contents exchange to support different cases, we need to consider the knowledge flow for different learning frameworks. One example of knowledge flow would be the flow of sharing of models between the network and the UE. Different learning frameworks have different knowledge flows, and each different flow should be supported with a unified framework. Lastly, it is important to note that feature-by-feature self-evolving will lead to discrepancies in the long run. Therefore, the long-term evolution of the system itself is also a key part of the unified design process. Let's now dive into more details. Firstly, a unified native lifecycle management should be designed with common management signaling and procedures. For various use cases, typical logical nodes for the lifecycle management should include the data source nodes, inference node, training node, and management node. The common signaling and procedures for different use cases can reuse these nodes as much as possible. One important part of this is having a unified data collection solution that can be achieved by using specifically designed data plane as seen in the figure on the right. The design of such a data plane needs to consider various requirements from different use cases. For example, aspects related to data content, data size, and latency requirements. With this kind of unified design, we can prevent duplicated data collection while satisfying various data collection requirements with minimum resources. This unified LCM will allow us to achieve a future-proof, efficient, and elegant protocol architecture. Now, I want to move to our next design principle, which is related to spatially distributed AML capabilities across different entities. With the fast development of AI technologies, AI/ML capabilities would ubiquitously exist in network entities. The whole system architecture and the procedure and design should take this into account. We have developed a high-level architecture design as below, considering AML capabilities at UE, base station, core network, and operation administration management system. This kind of a distributed AI system design not only makes full use of AI capabilities in all entities, but it also provides a good solution for data privacy and data security protection. Since cooperation among different entities is able to leverage local ML capability and reduce some unnecessary exchanging of data. To achieve proper management of distributed intelligence, resource sharing among different use cases within a single device should also be paid close attention to, since cooperation among entities would be impacted by such dynamic change of available resources for each use case. Next, let's move to the knowledge flow between entities for different learning frameworks. Different learning frameworks need to be supported for various use cases. The exchanged content and exchanging procedures will be different for different learning frameworks. Thus, the knowledge flow for different learning frameworks will also be different. For example, for federated learning, the models need to be first shared from the network side to UE, and based on the local training, the model is then fed back to the network again. While for supervised learning, the learned models may only need to be transferred from the network to UE if the model is trained at the network side. Interaction between different entities need to take all these different knowledge flows into account. And finally, I want to share with you our vision of a self-evolving capability of a 6G AI. The automation of a 6G system holds great promise and is a key priority for vivo when it comes to the convergence of AI and communication. The potential for the self-evolution of 6G AI is particularly exciting. through the automation of collected data, extracted knowledge, and iteratively interaction with the environment, we can expect the 6G AI will be able to update and eliminate old modules as well as derive new modules itself, gradually building a more efficient communication system through self-evolution. At its very basic level, self-evolution will allow for automated update of model parameters. On a second level, we are also expecting that model hyperparameters, such as number of layers and the structure of the model, can also self-evolve automatically. If we go even further, we can expect that use cases within the system can self-evolve. For example, AI itself will be able to generate a new use case and even merge multiple use cases into one. By self-evolving, the 6G AI system will continuously improve itself to achieve optimum results, allowing Vivo to provide our customers with the ultimate user experience. Now, we are coming to the end of today's presentation. We believe that the interaction of AI and wireless communication will bring users a more intelligent, seamless, and stable user experience in the 6G era, and we look forward to better serving our customers through the convergence of 6G and AI. Thank you all.
Thank you all for your such an insightful presentation and demonstration. Building on that, our next topic explores integrated sensing and communication, ISAC. The integration of telecommunications and sensing technologies with smartphones and 6G systems has the potential to spark a revolutionary change in the way in which we interact with the world. Our 6G director, Jiang Da-jae, will expand upon this topic. Welcome, Da-jae.
Thank you, Rakesh. Hello and welcome. It's a great honor to be here with you, our industry partners, to share about Vivo's research and technological achievements in the area of integrated sensing and communication, also as known as ISAC. Today, I will introduce the ISAC from the following aspects. The first is the use cases and the system architecture. ISAC refers to one system to provide sensing and communication functions, to utilize the resources efficiently, and even to pursue mutual benefits. ISAC can provide spatial information about unconnected objects, as well as the connected devices and their movements and surroundings. ISAC will play an important role in many scenarios, such as the low-altitude drones, the industrial automation, the medical and healthcare, and the warehousing and logistics, and so on. Two example use cases are the personal health monitoring, such as the sleep quality monitoring, and the intelligent transportation. For example, the pedestrian detection and the vehicle speed detection. Okay, this is the overall system architecture for ISAC. At the bottom of the chart, the 6 basic sensing modes, including the base station monostatic sensing, the base station to base station bistatic sensing, base station to UE bistatic sensing, and so on, are illustrated. There are various kinds of sensing use cases. The target of the 6G ISAC is to support all the use cases through a unified measurement framework, rather than a case-by-case design. At the top of the chart, the sensing control function and the sensing data processing function will be supported by the network. Regarding the different sensing modes, we have carried out some simulations to compare the sensing SINR performance between the base station monostatic sensing and the UE to base station bistatic sensing in indoor scenario. For the UE to base station bistatic sensing, the UE are randomly distributed in a circle, centered on a sensing target. The simulation results show that UE-based sensing can improve the sensing performance compared to base station monostatic sensing, especially in the poor coverage region. And now, I'm going to go into more details about some of the key technologies of ISAC. For the ISAC waveform design, there are three directions. The first is the waveform for communication. For example, the OFDM, the DFTS OFDM, and so on. The second is the waveform for sensing, such as the well-known FMCW. And the third one is the waveform for ISAC, for example, the OTFS. Regarding the sensing signal patterns, compared with regular signal patterns, irregular pattern design, for example, the Costas pattern, is important because it can help to achieve better results with lower overhead. Okay, the multi-band sensing refers to the joint acquisition and processing of sensing data on different frequency bands, which can obtain more comprehensive and accurate sensing results. There are multiple technical directions for multi-band sensing. You can collect different sensing measurements for different bands. You can also gather the same sensing measurements for different bands. And the two-step sensing. The two-step sensing here means the lower band for coarse-grained sensing and the higher band for fine-grained sensing. The challenge of the multi-band sensing is that there may be some random initial phase problems in different frequency bands, and this can affect the coherent processing among the different bands. Multi-antenna ISAC system is the integration for MIMO and ISAC. The typical hybrid analog-digital multi-antenna architecture for sensing consists of two parts. Part 1 is the analog beamforming, which can generate a beam directed at the sensing target to obtain the beamforming gain. And Part 2 is the digital beamforming, which can form a virtual array to achieve a higher sensing resolution. Compared with the monostatic sensing, the bistatic sensing involves more nodes for sensing and can achieve a diversity gain. Furthermore, more and more nodes can be involved in the sensing, which creates a coordinated multi-point system for ISAC. In a comp ISAC system, different levels of the sensing data can be collected in one node to generate the final sensing results. The table here shows different levels of sensing data. There is a trade-off between the amount of the sensing data aggregated and the sensing accuracy of the comp ISAC. In order to achieve the optimal allocation of resources while meeting the sensing performance requirements, the resource allocation of the sensing signal needs to be adaptively adjusted according to the sensing measurements. This can improve the overall system efficiency of ISAC. Network need to adjust the resources of power, time, frequency, and space according to the sensing measurements, including the sensing SIR, the measurement results of the Doppler and latency, and so on. One example is that as the target, for example the person, gets closer to the UE, the density of the sensing signal needs to be smaller. To ensure a continuous user experience of ISAC, mobility management for ISAC is essential. Due to the movement of the sensing target and the sensing nodes, the best sensing nodes for sensing service need to be changed. This is very similar to the handover or the cell reselection in communication. The procedure of the mobility management for ISAC include 4 steps. The first is to determine if the condition for switch of the sensing nodes are met. The second is to determine the new sensing nodes. And the third one is to send the sensing context and the configuration to new sensing node. And the last one is that the new sensing nodes start sensing. Sensing non-ideal factors are caused by the imperfections in devices. It can lead to serious measurement errors, which in turn affects the sensing accuracy. Sensing non-ideal factors include the time offset, the carrier frequency offset, the RF channel inconsistencies, and the time domain random phases. The corresponding method to solve these issues include the common clock calibration, the channel C30 ratio of the two antennas, the reference path, and finally the round-trip time-based method. Some of the information obtained from sensing may be private, and there is a risk of information leakage. Therefore, it's necessary to regulate the application of sensing by appropriate rules and processes, as well as adopting effective technical means to protect the sensed information and prevent privacy leakage and other security issues. This can be done, for example, through the sensing encryption, the sensing obfuscating, the enabling and disabling of the sensing function, as well as sensing authorization and authentication. Now, I will give some brief introduction of the ISAC channel measurement and prototype. The sensing channel model is important when it comes to evaluating the performance of the sensing technique. We conducted a sensing channel measurement for respiration. These tests were conducted indoors. The key is to obtain the power of the relevant path for exhalation and inhalation. We also conducted a sensing channel measurement for human body falling down. These tests took place indoors. The channel characteristics, for example, the delay and the power output was different depending whether the people was kneeling or lying down. And now we are going to conduct a prototype demonstration to show you the practical applications of the ISAC and to provide you with a better understanding of this technology. I hope that you enjoy it. Welcome my colleagues, 丁胜利、李建之 and Yao Jian.
With the increasing research and application of radio wave for sensing, the ubiquitous communication signals have become a huge treasure trove to be exploited. The integrated sensing and communication ISAC prototype of base station BS monostatic sensing mode includes a 6G BS and a 6G user equipment UE. The 6G BS supports trajectory tracking of the target in BS monostatic sensing mode. At the same time, two-way high-speed communication is realized between the 6G BS and the 6G UE. The prototype operates at the center frequency of 4 GHz and a bandwidth of 400 MHz. The prototype works according to the following procedure. Firstly, the BS sends out signals, which are partially reflected by the sensing target, and then bounced back to the BS. The self-interference is eliminated by isolating the transmitting and receiving antennas. The BS can calculate the distance, speed, and angle to achieve real-time precise positioning and trajectory tracking of the target. At the same time, part of the signals are received and processed by the UE for downlink data communication, and the UE also sends signals to the BS for uplink data communication, realizing a two-way high-speed communication. The computer shows the constellation diagram, uplink and downlink of data communication throughput, as well as the results of target trajectory tracking in real time. Now, let's see what else we can do with the ISAC. This is a prototype of a health monitoring equipment in BS to UE bistatic sensing mode. It supports respiration monitoring and two-way data communication between the BS and the UE. The center frequency of the prototype is 3.6 GHz and bandwidth is 100 MHz. Part of the signals sent from BS are reflected by the human body and reach the UE, and part of the signals reach the UE directly. Through a series of sensing algorithms and communication algorithms, results can be obtained and shown on the computer screen. So, on the computer screen, we can see the test results of the respiration rate of one person, as well as the simultaneous online streaming service. Apart from that, there are other sensing modes. Let's go on. This is our coordinated multi-point ISAC prototype. It features the sensing capability for trajectory tracking based on the coordination between multiple UEs in BS-UE bistatic sensing mode. The prototype operates at the carrier frequency of 4 GHz and a bandwidth of 400 MHz. In this prototype, the 6G BS in front of me is transmitting communication signals and channel state information reference signal. At the receiver side, the 8 receiving antenna ports are divided into 4 groups of 2 ports each to simulate 4 6G UEs deployed in different locations. Based on the downlink channel estimation, the UEs can obtain the Doppler frequencies of the signals reflected from the sensing target and report them to the same computer. The trajectory of the sensing target is eventually obtained by the computer after signal processing. It is conceivable that with the empowerment of sensing capabilities, the future 6G system will bring us a more convenient life. In the city of the future, 6G system guards the safety of low altitude and guides everyone's way home through smart transportation. Upon we arrive home, intrusion detection and fall monitoring can ensure personal safety. Gesture recognition can help us control various devices and appliances. And respiration and heartbeat monitoring can keep an eye on our physical health and provide advice on our well-being.
Thank you all for the deep insight into this exciting field. The application possibilities for 6G are endless, and to achieve this vision and better serve the needs of consumers, we need intelligent network architecture that will enable personalized, high-quality experiences that meet a vast array of users' needs. Here to share Vivo's latest insight on 6G network architecture is our 6G specialist, Yannan. The time that follows will be handed over to Yannan.
Hello everyone, it's a great honor to share Vivo's thinking on 6G network architecture and services with you, our industrial partners. In this presentation, I will introduce Vivo's design principles overview and key technologies of 6G network architecture. Well, there are 3 main design principles. First of all, when designing the 6G network architecture, we believe that we should improve 5G existing network performance and quality of service, whilst keeping its inherent advantages. While 5G has many advantages, the service-based architecture, for example, allows for the combination and the deployment of different services. It can also help to avoid duplicate deployment of network functions and enable rapid innovation of network services. 5G introduced many new features to the basic communication functions, such as artificial intelligence, non-terrestrial networks, positioning and sensing, ambient IoT, and so on. These features are still important for 6G. What's more, 6G needs to consider how to natively support them at the first release. When we design the 6G network architecture, we benefit from these existing advantages, whilst driving further improvements in areas such as scope and granularity of network function, as well as transport protocols. Okay, the second principle is to meet the new requirements of 6G. The new requirements of 6G come from new scenarios, new services, and new technologies. In the 6G era, mobile phones will provide a more colorful world for everyone. You may enjoy engaging with personally customized virtual humans, the metaverse, as well as the freely connected and physical and digital integrated world. Okay, the third principle is to enhance basic capabilities, including reducing costs, increasing flexibility, achieving a higher security performance, and providing a better user experience. Well, for 6G network architecture, let's start from the overall topology. 6G will have the ability to adapt to various topologies without loss of performance, including centralized and distributed deployment, terrestrial access and non-terrestrial access, 3GPP access and non-3GPP access, as well as Internet of Things and Internet of People. While drawing an analogy with control plane and user plane, we think data plane can be introduced in 6G. The three planes with new functions are used to support native features and provide network services. As the figure shows, the system functional architecture includes the service layer, function layer, and the resource layer. Both 3GPP-defined service subsystems and OTT servers are included in the service layer. The function layer mainly includes function definition of the UE, run, and CN. The end-to-end procedures are also included in function layer. The existing communication functions such as access management, session management, UP data transmission need to be enhanced for 6G. Meanwhile, new network functions need to be added, such as sensing functions, computing functions, data functions, and almost zero-power IoT functions. Well, in addition to traditional spectrum resources, the resource layer also needs to include computing resources and storage resources. Okay, in order to present the overall 6G architecture in a visual way, we have attempted to provide an example of the 6G network architecture based on a series of assumptions. For communication functions, we have assumed the adoption of current 5G standards without reflecting the further enhancement that will be brought by 6G, because many different potential evolution options are still under discussion. Data functions, sensing functions, computing functions, AI functions, and security functions are introduced in the service-based architecture. While the existing SBA is mainly used for the interaction of control plane functions. Considering the efficiency of data transfer, a messaging framework is a potential option to support a large amount of data transfer in the call network. Correspondingly, RAN and UE also need to introduce peer functions to support the new features of 6G. Okay, next, let's go deeper into the key technology that Vivo is studying. The first one is native network intelligence. In 5G, network intelligence was discussed and standardized case by case in each release. For 6G, call network, radio access network, user equipment, and network management system shall natively support AI capabilities at the first release. The common framework and procedures for 6G network architecture are designed for enable all use cases and AI lifecycle management, while for 6G integrated sensing and communication (ISAC), all sensing modes, which are shown in the figure, shall be supported. There are various kinds of sensing use cases. The target of 6G ISAC is to support all the use cases through a unified framework rather than standardization case by case. Therefore, common sensing measurements and intermediate results should be prioritized, while data collection and data transmission are the common requirements of network intelligence and sensing. Data service or network exposure capability also relies on the data of 6G in order to avoid control plane carrying a large amount of non-signaling data, and to avoid user plane transmission terminating inside the network. The data plane was introduced. The data plane functions are used to support full lifecycle management of data, including data privacy and security management, data queues management, data collection coordination, data transmission and forwarding, data processing, and data service. The design of the efficient protocol stacks among UE, RAN, and CN is important, especially the air interface protocol stacks of the data plane. Okay, 6G is not only for Internet of People, but also Internet of Things. In order to support almost zero-power IoT, 6G network architecture should co-design lightweight IoT and high-capacity Internet, including both RAN nodes and user equipment as readers. The reader acts as an agent. On one hand, the reader can process complex procedures with the network. On the other hand, the reader can convert the procedures into minimalist air interface for IoT devices. While the 6G satellite integrated network is used to meet the growing requirements for direct satellite connection from UE. In order to improve the user experience, we adopt the design of unified UE and unified core network so that UE transparent satellite communication can be supported. Joint control and optimization of computing and communication are the core of convergence of mobile network and computing. There are three potential technical options. Two options are based on the enhancement of 5G architecture. One is based on the enhancement of edge architecture. The other is based on the enhancement of AMS architecture. The alternative is that 6G natively supports computing control and computing network better. Okay, 6G is going to be packed with many cutting-edge technologies. How will our customers use and benefit from 6G? Well, the convergence of mobile network and computing will help to solve many existing issues and unlock so many possibilities. One more question. Have you ever been in a situation where your phone cannot support a newly released game? Do you sometimes wish that you could experience higher performance real-time image recognition on your mobile device? The convergence of mobile network and computing will overcome the existing hardware limitations to allow our customers to enjoy the most optimum experience. Okay, now please join us to enter our lab and experience the magic of a 6G powered future. Welcome our communication technology engineer, Cai Jianan.
With the continuous evolution of communication networks, we can experience more and more services. Plenty of services need to be supported by a powerful computing platform, and thus computing power has become an important resource. We hope that in the future, computing power will be as accessible as traffic on a mobile network. As soon as people turn on their cell phones, computing power will be at their fingertips. In the prototype of integrated computing and communication here, the core network supports computing control and offers real-time computing service to the UE. It works as follows. Firstly, the UE sends out a service request for image recognition and transmits the video captured by the UE camera to the network in real time via the computing bearer. Once the core network receives the request, it will offload the image recognition task to appropriate computing servers, taking into account the communication and computing power status information. The neural network of computing servers will process the video data for image recognition. The final result data is then sent to the UE via the air interface. If you run an image recognition service on the UE, we have to use a simplified neural network due to the hardware capacity of the UE. It will lead to inaccurate recognition results and enormous power consumption. However, if we leave the job to the integrated computing services provided by the mobile network, the user can enjoy real-time image recognition services anywhere, anytime. In other words, in the future, smartphones will no longer be limited by their own hardware and will be able to dynamically leverage the computing power anytime, anywhere, to experience online gaming, 3D interactive virtual humans, extended reality, and etc.
Thank you, Jianan, for the wonderful presentation. Before we conclude today's event, I would like to invite Qin Pei, President of Vivo Communication Research Institute, to share a few words.
Good afternoon, everyone. Thank you for joining us today. Before we conclude the event, I really want to take a moment to express my sincere gratitude to our colleagues. Thank you for sharing your views and insights today. The breakthrough ideas and discussions we heard earlier were truly inspiring, and I must say I'm very excited about the future of the 6G system. At Vivo, we always believe that technology should serve humanity and enrich our lives in meaningful ways. This philosophy drives us always to explore new frontiers for a customer-first perspective. Reflecting this idea, the series of white papers are launched today explore 3 core concepts we believe will help shape the 6G user experience: convergence of AI and communication, integrated sensing and communications, and 6G network architecture. With convergence of AI and communication, we delved deep into 6G native AI technologies to help optimize network connectivity, enhancing signal transmission to achieve what matters to our customers most: more stable and smoother network connection anytime and anywhere. Integrated sensing and communications describes our waves on new avenues for innovation that will open up with 6G wireless electromagnetic waves. Just imagine 6G communication systems can additionally respond to healthcare systems that provide personalized care like never before, and smart-driven solutions that streamline your everyday tasks. This possibility to 6G sensing are endless. More importantly, 6G network architecture walks us through the design principle for 6G architecture. 6G will be constructed with inherent of 5G advantages, plus new services and new technologies, including data service and data plan, convergence of mobile network and computing, native network intelligence, ambient IoT, terrestrial satellite network, and etc. The Vivo Communications Research Institute has been hard at conducting research to gain a deeper understanding of the opportunities that 6G presents and the challenges we need to overcome to make it a reality. As a result, in the last few years, we released several 6G white papers that have become essential reads for anyone interested in 6G technology. Our findings are detailed in Digital Life 2030 Plus, 6G vision, requirements and challenges, as well as 6G services, capabilities, and enabling technologies. As we shape the standards and technologies that are said to enable higher bandwidth, lower latency, and stronger connectivity, we must think about we are going to translate these technology advantages into tangible user experience for the next decade. To that end, we see a world of incredible possibilities for our consumers: faster connection speeds, more intelligent applications, a thriving IoT ecosystem, and the seamless integration of augmented and virtual reality. And most importantly, we must also focus on security and privacy, and ensuring our users can trust the technology that powers their lives. Vivo's vision for 6G is clear: a freely connected physical and digital integrated world. We are excited about the journey ahead, and we are committed to make this vision a reality in collaboration with our industry partners. I'm confident that together we can bring you a boundless, connected, intelligent world. Thank you.
Thank you, Xinfei, for your inspiring words. At Vivo, we are dedicated to innovating and delivering cutting-edge technologies that create a seamless bridge between people and the digital world. 6G may still be far from our grasp, but endless possibilities it promises can profoundly influence our lives and everything around us. Thank you to our experts for their hard work, and thank you to all of our participants today. We look forward to seeing you again next time. Have a great day.